So we were talking about chapter 14 out of that packet, girders, sill plates, bridging, floor joists, and stuff. I'm going to do the first two examples here just to see how you're doing. That third one's probably a little more complicated than I would ever ask you to do. So we have 30 feet here, 20 feet here, 28 feet, and 18 feet. And our only beam, they're giving us a girder across here, and they're showing a post. Now, they're not showing any dimensions on the post, so we can assume the post is centered. So I'm going to start off with girders. We said for girders we would go up to what length? 24. This is 18 feet, so we just need 3 18-footers. Not much of a girder build up there, is there? For sills, how did we find the sills? The linear footage of sills needed is simply the perimeter. So the perimeter of this is going to be what? This over here is 46. This piece is 10. So if I add up all those sides, 30 plus 46 plus 20 plus 28 plus 10 plus 18. What is that at 152 feet of sills. Whether that's 2 by 6, 2 by 8, 2 by 10, whatever you decide to use for it. Treated, of course. Any questions on that part? So next we're going to talk about the joists. We have two different runs for our joists. We have this run here, and then we have the long run. Let's do the short run first. We are going to assume, I don't think I specified before I sent you home with this one last Thursday, but we are going to assume that there is joists on the ends, that there's end joists. Rim joists we'll figure in separately. But anyway, for our 18 feet, our 10-foot span, I should say. Oops, come on. So it's 12 over, we're assuming a 16-inch spacing still. 12 over 16 times the run of 18, and then plus 1, minus 1, nothing. Because we need 1 on both ends, it's plus 1. Now this is going to come out to a decimal, which means we're going to have to round up because 18 is not modular. So 12 divided by 16 times 18 gives us 13.5, plus the 1 is 14.5. So that rounds up to 15 of the 10-foot joists. That's the only run for the 10-footers. So next is the 20-footers. So for the 20-foot span, what's the run of those? The run, of course, is this way. How far is that? 46 feet. So 12 over 16 times 46. Plus 1 minus 1. It is plus 1, because again, we'll need 1 on each end. 46 is not modular either, so this is going to come out to a decimal, so we'll have to round it up. 12 divided by 16 times 46. 34.5 plus 1 is 35.5. So that'll be 36 20-foot joists. So that's what we need for our joists. 12 over the 16 is the on-center spacing. 12 is just to convert it from inches to feet. So 12 over 16 is 3/4. of a foot. That's 3/4 of a joist per foot is what that comes out to be. So 3 joists for every 4 feet. And then, of course, we need rim. Rim joist is just by footage. Need rim joists here, here, and here. This piece right here is already figured in as one of the 10-foot joists. Got put there. So that's 46 plus 18 plus 28 is 92 feet of rim joist. May or may not be the same as the regular joist because it doesn't have to free span anything. Any questions so far? Does all look familiar? Okay. When do we need bridging on a joist? If the span exceeds 10 feet. Right? So do we need bridging over here? Those are exactly 10 feet. We're going to say no for now. It really all depends on building inspector and interpretation. Some will tell you that at 10 feet, you need bridging. Others will say it has to be more than 10 feet. The reason the code says 10-foot free span, it all depends on how that is interpreted. Because if you look at this area here, it is the 10 foot is typically going to be measured from the outside of the wall to the center of a girder. Well, there's going to be at least a 2x6, if not 2x8 or 2x10 sill sitting there, and then whatever half of that girder is. So your free span is only going to be 9'4", 9'3", somewhere in there. So it's not 10 over 10 foot. It's not a 10-foot free span. But some inspectors will interpret your free span from end of beam to end of beam, regardless of what the bearings are on it. So the only place that we need bracing or bridging is right here, the 20-footers. It's questionable on 20 feet also whether you need 2 rows of bridging or not. We're going to say just 1 row. If it was 21 foot, we would have to have 2 rows of bridging. At 20 foot, at 19, you only need 1 row of bridging, but at 20 foot, again, it's questionable whether you have to have a second row of bridging in there or not. We're only going to go 1 row of bridging, so it's going to be 40. The run is 46 feet. So the amount of bridging is 3 times the run. So 3 times 46, which is going to give us, 138 feet of bridging material. Typically, that will be a 1x3 or 1x4 bridging material or some sort of metal bridging. Finally, floor. Now, I had told you guys just to go ahead, find the area, and then do what to it? Well, let's just go ahead and find the area. So for the area of this, we got piece 1 here that is 46 by 20, that rectangle. Oops, not sure what happened there. So 46 feet by 20 feet, so 920 square feet. And then over here, 10 by 18. For 180 square feet. Adds up to 1,100 square feet of area. How do we find the number of sheets of flooring from that? Yep, the sheeting is 4x8, so that would be 32. So over here we divide by 32. Come on. So 34.375. So we would round that up to 35 sheets. Now we know that that's not realistic because tongue and groove sheets, you can't just flip around and reuse them in whatever position. Like I said, for what we're doing, that would be the correct answer. But if I were actually figuring this out on a job site, let me get rid of some of this mess in the middle here. What I would do would be this. This is 20 feet. That is modular. So that's good there. However, this is 46 feet. That's not modular. So I would extend it out an additional 2 feet to make that 48 feet. So the area I would find here would be 20 by 48. Have a good one. So 960 square feet. Over here now, 18 is not modular, but if I extend it out to 20, it would be. 10 is not modular either, so I'd extend that out to 12. So I would actually figure that out as 12 by 20. So 240 square feet, which ends up being 1,200 square feet of area. And 1,200 square feet divided by 32 can give us a little more, 37.5 or 38 sheets. You might be able to use a few less than that if you really push it with your scraps. Like you might be able to use some of these 2-foot scraps here to do the end here, so you wouldn't have to extend that out to 20 feet. But if I were estimating, that would be how I would estimate, is I'd expand every dimension out to where it's divisible by 4 and then work off of that. Okay, so we said we'd do 2 of them. Let's do the second one. Obviously not drawn to scale. First thing I'm going to do is I'm going to add these all up to get 56 feet on this side, just because we're going to need that at some point. We said to always assume that the girder goes in the center of the longest span, right? So our girder is going to go here, splitting this into 16 and 16 feet. Like that. Now there are 6 posts here drawn in. 6 posts, of course, means how many spans? There's an extra one on the end, right? So 7 spans. So 56 divided by 7 means each of those is just 8 feet as we go up through there. So if we're using 24-foot material, we can do that's 24, 48, and then 8. Then going the other way would be exactly the same. And then we'd come back. All 3 layers would be the same, just starting from opposite ends. So for girders, we need 6 24-foot pieces and 3 8-foot pieces. Does that make sense? You look confused, Ben.
No.
Okay. For sills, remember sills is just the perimeter, so go ahead and find the perimeter of that for me. What'd you come up with? 166 seems a little short. At a glance, I'd say 184, but let's, you got 184? Okay, so 184 feet of sills, just adding up the perimeter all the way around. Perfect. Joists. So we have 3 different spans of joists here. We have the 16-foot span here and here. It's tempting to combine them into the same run, but we cannot. So for our joists, we're going to go 16-foot span. Our first run is, how much is this run here? 56 feet. And of course, we need one on both ends. So assuming 16 inches on center, it'd be 12 over 16 times 56, plus 1 because we need one on both ends. So we get 43 there. Now we need this one here, has a run of 18. Is 18 modular? It is not. So that means we're going to get a decimal. But we only need a joist. We need the end joist here. There, we do not necessarily need one here because it won't work out on our spacing. So what we are going to do is we're going to use a, that is not what I wanted. Let me undo that. There we go. We are going to use a rim joist there. Here. And we're going to let the joist fall wherever the spacing comes to. Which means we're still going to round up, but we're not going to add one for the very end. So there'll be one on, keep doing that. One on one end, but not the other. So it'll be just a 0. Hopefully I can stop erasing my stuff. So anyway, for the 16-foot span, it'll be 12 over 16 times 18, and no plus 1, but it's just going to be rounded up. So 12 divided by 16 times 18 is 13.5, so round up to 14. So that means we need 57 16-foot joists. And what that means over here is that last joist is probably going to end up somewhere in here like 8 inches away from that piece of wall. Next, we'll do the 10-foot span here in the middle. So this piece right here. Well, in that 10-foot span, it's a little weird because the first joist is not going to be at the end. The first joist is going to be here. But technically, it still counts as one at the beginning. So it's still going to be a 0. We're not going to subtract 1, but we're not going to add 1 either. The reason is because of the odd spacing, we have to have that extra joist there. The last one then over here should come out in the exact right spot so we can pick up with the 20-footers. So that'll be 12 over, I don't know why I put 18 there. That should have been 12 over 16. I typed in 16 in the calculator, but times, what's the span, what's the run there? 18. So that'll also be 13.5, which rounds up to 14. So there'll be 14 10-foot joists. Wow. And then finally we have the 14-foot span down here, which has a run of 20. 12 over 16 times 20. I need one on this end. Am I going to need one on this end? Yes, we will. In fact, being modular, that joist will come out exactly on that edge. Now, by exactly, I mean within 3/4 of an inch. If we're assuming we're using like 2x10 or 2x12 material, you are allowed, and from the engineering side of things, you're allowed to move a joist by half of its thickness. So if an 1.5 inches thick, you can move it over 3/4 of an inch. The reason they do that is because technically on 20-inch spacing, that joist would be did it again. Maybe it won't let me undo it this time. I can just draw it back in. So anyway, I'm erasing more. Oops. Now I'm drawing it wrong. There. Close enough. Technically, at 20-inch spacing, that joist would actually hang off the edge. The center of the joist would be right at the 20-foot edge. But we're allowed to move it off half that thickness so that it does line up with the edge. Otherwise, you end up having to put, what you end up doing is you put a short joist here, and then you put a rim joist here that's offset, and that's just awkward. So it allows you to put them in there so that they fit in. So anyway, that is going to be a +1. We're going to put 1 on both ends. So 12 over 16, that should have been times 20. All sorts of flustered today. So 12 over 16 times 20 is 15, plus 1 is 16 joists. So we need 16 of the 14-foot joists. And then for rim, we need 56 feet here. We need, these add up to 56 feet over here, but there's one more piece that we need. Remember, we had this little piece. So that was, what, 8 foot? 6 foot. 6 foot. So we got 56 plus 56 plus 6. Ends up being, what is that, 118 feet of rim joist. Not so bad? So the difficult part is these being not modular here, trying to figure out, is it a +1 or a -1 with that joist in there? Generally, like I said, if you're not going to put an extra one on the end, it's a 0. You add nothing to it, but you round up is the way you handle it. For bridging, obviously this span is more than 10 foot. So that's 56 feet. This is more than 10 foot. That's another 18 feet. Is this more than 10 foot? It's exactly 10 foot, right? So that one we're not going to need, but this is more than 10 foot, so that's another 20 feet. So if we add that all up, is that 94 feet of run that needs bridging? So bridging is going to be 94 feet times 3, or 282 feet. And finally, flooring. So the area of this, really the simplest way to do this area is going to be to cut it into 3 rectangles like that. This one is 18 by 32. Which gives us, what, 576? Yeah, that looks right. This one here is 18 by 26. Which is, what, what, 468. And finally, this one is 20 by 30. That one's easy enough. For 600 square feet. We add that all up. $1,644 square feet of area. And what do we do to that? Divide by 32. So 51.375 or 52 sheets. Now again, looking at this, the 32 is fine. I would have expanded. Let's make this mess go away. I would have expanded this out to be 32, and I would have bumped this out to be 28. I would have bumped this out to be 20 and this down to 16 then. And those would have been, I would have used those areas to find it. But again, we're not going to get that exact in here. When you take your estimating class next year, you can worry about all those allowances for modular and stuff. Some people actually, I've always been one that I just bump it out to modular dimensions and figure it off of those modular dimensions. Some people use like waste margins. Like use a 10 or a 15% waste margin if it's all modular. If it's not modular, they bump it up to a 25% waste. So there's different ways of handling it. Anybody have any questions on finding the girders, the joists, the bridging? Okay. So today we're moving on to the next step. We want to find studs. And we're just going to focus on exterior walls. So if I have a house, let's call it 32 feet by 48 feet. If I want to find the number of exterior wall studs, I have two different calculations. I have a base calculation, or a base amount. And that base amount, the number of studs is 12 over my on-center spacing times the perimeter of the house. Well, my on-center spacing for wall studs is typically 16 inches, right? And so here we just need to find the perimeter. The perimeter is going to be 160 feet, correct? If I add that up. So that means the estimated number of studs is 12 over 16 for the on-center spacing times 160 feet gives us 120 studs. Now remember, that is the base amount of studs. Then, on top of that, there is an adjustment. Now, the adjustment only increases the number of studs. You don't get less unless you have like huge windows and stuff. We're not going to calculate anything for that. But for our adjustment, it is plus 2 for each corner. So here, how many corners do we have? 4. So 2 times 4 is going to be a plus 8 for the corners. Why is it plus 2 for each corner? Well, 1, for a given wall, We said this 12 over 16 or 12 over the on center times that length gives us studs at the spacings and one at the end. It does not give us one at the beginning. So one of that plus 2 is to do the stud at the beginning. The second one is on every corner. You have walls that meet. One wall has to be lapped over and one wall has to be butted up. So the standard calculation puts a stud here and then wherever it's spaced. It puts a stud here and then wherever it's spaced. But when you go to do your sheetrock inside, what are you going to need to do here? You need to nail something, right? Depending on who you talk to, some people say sheetrock can free span like 6 inches. Some say 8 inches. Half-inch wall sheetrock, I would not span more than 6 inches. I usually don't go more than 3 or 4. So you need a stud there because this is going to be 10 inches from here to there. You're going to have an extra stud there. So typically, that's what the second one is to put a stud here. I usually leave it, some people put it right at 5.5 inches. I usually put it at 6.5 so that you have an inch here so you can get into that corner. And if you forget to insulate it before you sheet the outside of it, which a lot of people do, you see a lot of houses with cold corners, or they drill holes and shoot it with foam. Really hard to figure out how much foam you got in there. I've also seen people pop their exterior sheeting right off because they put too much foam in there, and as it expands, it blows it right out. So I always leave a 1/2 inch. Either you can then push fiberglass insulation in there, or if you do come to spray it with foam, you do a quick spray, you let it expand, you come back and you can spray it again through that little crack. And you can see exactly how much it's filled up. The next adjustment is +1 for non-modular walls. The packet just says for any odd length wall. By odd length, it means non-modular. So modular, just a reminder, modular means divisible by what? By 4. Are any of the walls on my sample one here non-modular? No, 32 and 48 are both divisible by 4. So this is going to be a +0 because none of those are non-modular. Now the rest of this is going to require me to do a little bit more drawing. So I'm just going to do a simple little plan here. Yeah, we'll leave the rest of it open. So this next one is +1 for interior, they call it partition, this is interior wall intersection. So here we have 1, 2, 3, 4, 5, 6 interior walls intersecting the exterior wall. So that's 1 times 6, or +6. Why would you have to add studs for an interior wall hitting your exterior wall? Well, once again, here, let's say there's my normal stud spacing, but my interior wall hits it like right there. So there's going to be a stud on the interior wall here. I can nail when I put in sheetrock. I'll be able to nail here. But when I put in sheetrock from this way, there's nothing to nail to there or there, right? So often what is done is I take an extra 2x6 like that. It hangs over 1 inch in each direction. And that allows us, it gives us something to attach this wall to. We can actually nail through the end of the wall into that 2x6 so that it holds it in place. And then it gives us an inch lip on each side to nail our sheetrock to. The alternative to this, by the way, and I've seen it done more and more lately, and I actually really like it, is people do the outer shell. They sheetrock the whole ceiling. They sheetrock all of the outer walls, and then they put up the interior walls. That way they don't have to worry about how you're going to attach the interior walls. You can use 12-foot sheetrock on the whole thing, get the whole thing up, and sometimes they'll even mud the outside before they put up the inside just to have it done. The only disadvantage, there's no disadvantage on the walls. The only disadvantage to this is on the ceiling. If you're coming back to do electrical work, you have no idea where the walls are. Normally, before you insulate, you can go up there and you can see the top of the walls through the sheetrock. But if you sheetrock the whole ceiling, you can't see that. So it's a little bit trickier for the electrician. What you end up having to do is you have to drive spikes up through the top of the walls, or I usually would take like a 4-inch screw and drive it up through so it sticks up. And even that, it's only sticking up, 3/4 of an inch. It's a little hard to see. And then the final thing we need, I'm going to have to add a little bit more drawing here. We'll put in 2 doors. And some windows. +2 for each door or window. Now again, the +2 is because you got to have that jack stud on each side of your header. You might say, well, you just moved the long studs out. Well, you still need to have the base of the window framed and the balloon studs below and anything above if it doesn't match up above. You do end up you usually need 2 more studs. If you have a really wide window and you say, well, maybe we can get rid of some studs there. What is it now? Is it 60 inches? If a window is more than 60 inches, you have to have a double jack stud on the outside edges. So you still need the extra studs for it. So here we have 1, 2, 3, 4, 5, 6, 7 windows and 2 doors. So 2 doors plus 7 windows equals 9. So 2 times 9 equals 18 plus. We add all those up. 8, 0, 6, and 18 make plus 32, right? So we had 20 plus 32 is 152 studs. What do you think? Good stuff? Some of you are looking a little dazed. One of those days? It's Monday? Okay. We'll set that aside for now. We don't need to play with that anymore. Okay, so the next thing we need to look at. A little bit of review. Trying to remember how much we did with the integers at the beginning of the year. Didn't really do a whole lot with them usually in this class. So I want to review integers. Integers are just negative numbers, is all it is. It's our whole numbers, and we're not putting decimals or fractions with them necessarily. But they can be negative instead of just positive. And to work with integers, we need to go all the way back. We talked about, adding and multiplying and all that, dealing with the count and the name. We never really defined what it meant to combine counts. We just assumed that you could add or subtract or whatever. So to do that, let's represent the count of a number. So if I have a number that has a count of 6, how I would represent that? Typically on a number line. And there are actually a lot of different ways this has been done through the years. Dots or whatever. But the most useful representation, if you're going to calculate with it, is something called a vector. And a vector is pretty simple. It's just an arrow that starts at 0 and goes to the number, like that. That's the vector for 6. The vector has two things. It has a direction. It's either positive or negative. And then it has something called the absolute value. Is that a term you guys have heard before? Absolute value is just the length of the vector. So for 6, this is the symbol for absolute value. The absolute value of 6 is 6. The absolute value of -4 would be 4. So some people define absolute value as just the positive of the number. It's the magnitude or the length of the vector without the direction being considered. So now if I wanted to do a problem like 6 plus 2, I have the vector for 6 there. The vector for 2 is going to look something like that. Addition is mechanically combining the two vectors. So I take the vector for 2 and I'll move it and I'll put it with the 6. Or I could have done the other. I could have taken the 6 and moved it to the end of the 2. Either way would have worked. And I see that 6 plus 2, that ends up at 8. Well, we all knew that 6 plus 2 was 8. We did not need the vectors to do that. But what if this were not 6 plus 2, but 6 plus a -2? Now that parentheses there is not an enclosing symbol. It's just so that you know that's a -2 and not subtracting 2. So if that's 6 plus a -2, the vector for a -2 starts at 0 and goes to -2 like that. And so if I'm going to add those, I take that vector and I move it to the 6. And you can see I end up at -4, or not -4, +4. 6 plus -2 is 4. I do not keep this picture. I don't draw vectors every time I add integers. I don't expect that you're going to either. But I do keep that picture in mind when I'm working with negative numbers. For example, if I have a -38 plus 17, what I am thinking is this. Here's 0. -38 goes this way. Positive 17 goes the other way because it's positive. Does it have longer or shorter absolute value? Shorter. So it stops before we get back to 0. So this picture tells me two things. One is I ended on the negative side of 0. So my answer is negative. 2, the absolute values or the directions go in the opposite direction, which means the value of my answer is the difference in those absolute values. So 38 minus 17 is 21. This is a -21. Or if I have 43 plus a -64. So what I am picturing there is here's 0. 43 goes this direction, positive. -64 is the opposite direction because it's negative. Longer or shorter? Longer, so it goes past 0. So this tells me that answer is also negative. Because the vectors go in opposite directions, it is, again, the difference in their absolute values. So I take the bigger one, the 64, and I subtract the smaller one, the 43, giving me 21. That is also a -21. That was not planned, by the way. I might have a 28 plus a negative 19. So when I'm looking at that one, here's what I picture. There's 0. Negative 28 goes this way. Well, negative 19 goes the same direction. So that is definitely on the negative side of 0. Both of them go in the same direction, so their absolute values add together. So just 28 plus 19 gives us 47. So it's a negative 47. That makes sense? Does that look familiar at all? Maybe? Okay. Subtraction is where things get confusing. Subtraction of integers haunts people all the way up through algebra and all college algebra and all of that. Even in calculus, people struggle with subtraction of negatives. So if I start out with something like 8 minus 3. Get a number line drawn out here. If I asked you to draw out 8 minus 3, you'd probably draw something like this. There's 8 minus 3 brings us back to 5. Well, we all knew that 8 minus 3 was 5. We did not need the picture to do it. But if I look at that picture, some of you might pick out that picture looks an awful lot like the picture of 8 plus a negative 3. Because it is. Negative 3 would look something like that. If I took that negative 3 and I moved it with the 8, oh, there it goes. I'd get 5. The reason it looks an awful lot alike is because it's the same problem. We talked a little bit at the beginning of the semester saying subtraction is part of addition. It technically is a form of addition. It's defined as part of addition. That symbol right there acts on the number that comes after it. And subtraction literally means add the opposite. Well, what's the opposite of 3? Negative 3. So subtracting positive 3 is adding negative 3. Now, if we have positives like 8 and 3, there's no need to change anything. If I give you 42 minus 18, we know how to subtract. I would expect you to just get 24. There's no reason to change anything about that at all. But if it is a negative 37 minus 24, now it might be beneficial to make that change. The negative 37 doesn't change. The subtraction operates on the number coming after it. So instead of subtracting 24, we add the opposite of 24, which is negative 24. So here's 0, negative 37, negative 24 goes the same direction. That tells me my answer is on the negative side of 0, and I add the absolute values. 37 plus 24 is 61. The one that confuses the heck out of people is this one. 63 minus a negative 19. Well, we don't want to work with subtraction with integers, with negatives. So again, the 63 doesn't change. That's just going to be 63. The subtraction operates on the number coming after it. So I'm going to change the subtraction to addition. What's the opposite of negative 19? Positive 19, or just 19. So subtracting a negative 19 is just adding 19. Well, now we don't even need the vectors for that. We can just add those to get 82. Or we might have negative 54 minus a negative 73. So again, the negative 54 does not change. The subtraction operates on the number coming after it. So the subtraction is going to become addition. The negative 73 is going to become positive 73. So now my vector here is 0. Negative 54 goes this way. Positive 73 goes the other direction, longer or shorter? Longer. So that goes over into the positive side of things. The vectors go opposite directions, so we subtract their magnitude. So 73 minus 54 is a 19. So it's a positive 19. There is also a negative button on your calculator. Depending on which calculator you have, you will either have a button that looks like this, negative. You would press that before you enter the number. Or some calculators have, it's called a swap sign button. Looks like that. So you would enter the number first, and then you'd press that key. So to enter this up here, negative 54 minus a negative 73. If you have this button, you would enter 54, swap sign, minus 73, swap sign to make it negative, and then you'd hit equals. You've used it? Okay. You're good at it? Good deal. Multiplication and division are the ones that most people just have the rules memorized for, and I'm okay with that. But let's just show you where the rule comes from. For multiplication, we've talked about 3 times 5 is just repeated addition. 5 times 3 means we have 3 5s added together, giving us 15. Well, if that's the case, then negative 5 times 3 is easy enough to figure out. We have 3 negative 5s added together, which is negative 15. But how about 5 times negative 3? We cannot take 5 and add negative 3 of them together, can we? That just does not work. Well, fortunately, we've said that multiplication, we can switch the order of the numbers. It's what we call commutative. 5 times negative 3 is the same as negative 3 times 5. So now that's just saying, hey, take negative 3 and add 5 of them together. Which is negative 15. The one that doesn't work at all is this one, negative 5 times negative 3. Well, we've been taught, what is that answer that we've been told? Positive 15. We've been taught a negative times a negative is a positive. But if we look at our definition here, I cannot take negative 5 and add it together negative 3 times. I cannot take negative 3 and add negative 5 of them together. It just doesn't work. And this happens a lot in math, where the basic definition breaks down. We're going to see it when we look at powers of 10 next week or towards the end of this week. So what we do when the basic definitions break down is we use examples where the definitions work, and then we check to see if there's a pattern that we can use to define the result for what doesn't work. So let's start with negative 5. What is negative 5 times 3 again? Negative 15. So now for a pattern, we're going to keep things the same except for one piece. So I'm going to keep the negative 5 the same, and I'm going to change the 3. I'm going to reduce that by 1. What's 3 minus 1? 2. Yep. So negative 5 times 2 is negative 10. So we look what happened out here. We reduced that by 1. This went up by 5. So negative 5 times, if I reduce this by 1 again, what would I get? 2 minus 1? 1. Negative 5 times 1 is negative 5. Well, this went up by 5 again. So the pattern seems to work. So let's keep... What's that? Oops, I wrote down that. Thank you. Yeah, negative 5. Thanks. Let's keep going and see if the pattern keeps working. Well, negative 5 times, if I reduce that by another 1, it would be 0. What's negative 5 times 0? 0. Did that go up by 5 again? Sure did. So that pattern works. So negative 5 times, we reduce that again to a negative 1. This has to go up by 5. That would be positive 5. Negative 5 times negative 2. This would have to go up by 5 to be 10. Negative 5 times negative 3. Again, up by 5 to be 15. So the only reason when you multiply one negative times the second negative, you get a positive is because it continues the pattern. And so in math, we like to keep patterns going, so that's what we've defined it to be. The same is true with powers, something to the power of 0. That's defined off a pattern because it doesn't make any sense otherwise. So the general rule, if you're multiplying, if I have a negative, like negative 3 times a positive, like 8, my answer is going to be, first of all, positive or negative. Negative, a negative times a positive is negative, and 3 times 8 is 24. If I have a positive like 5 times a negative, let's just go with negative 4, the answer is going to be positive or negative. Negative, and 5 times 4, 20. Or if I have like a negative 6 times a negative 10. Negative times a negative will be positive, and 6 times 10, 60. When we divide, we have followed the same rules. If I have a negative like 12 divided by a positive like 3, my answer is, first of all, positive or negative. Negative, and 12 divided by 3 is 4. If I have a positive divided by a negative, 20 divided by a negative 4. Positive divided by a negative will be positive or negative. Negative, 20 divided by 4, 5. Or if I have a negative, like negative 18 divided by negative 6. A negative divided by a negative will be positive, and 18 divided by 6, 3. Well, why is all that so important? Well, because we're going to get into working with algebraic numbers now. I'm going to sense that's a little bit of fake excitement. Not an algebra fan? There's a lot of uses for algebra. It's just not many classes do a good job of showing you what those uses are. I'm not going to claim that I'm going to do such a good job either, but hopefully I'll point out some differences that make it a little easier to understand. So we've talked about variables and the different uses of those variables. So one of the uses that we're going to talk about today is as a place value. We have seen numbers in their place value. This is the ones, the tens, the hundreds, the 1,000s, and counting on up. But realistically, this is the 10 to the 0 place here. Or the ones, this is 10 to the power of 1. 10 to the power of 2 is 100. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth is 100,000. 10 to the sixth is a million, and on down the line. We have what is called a base 10 number system because the place values are exponents with bases of 10. The base of each of those exponents is 10. We've looked at taking a number like 4,629 and writing it out in that full form. And what we did was 4,000s and 600s and 2 10s and 9 ones. We often don't even write the ones because 9 is just a 9 whether it's ones or not. But we could have written that off, instead of writing out the words for those place values, we could have used the powers of 10. We could have written that as 4 times 10 to the third plus 6 times 10 squared plus 2 times 10 to the 1 is just a 10 plus 9. Well, if we write it like that and then compare it to an algebraic number, where an algebraic number might be 7 x to the third plus 4 x squared plus 5x plus 9, you can see the similarities. It's just here instead of the place values being powers of 10, here they're powers of x. And so when we go to do operations with them, we can do the operations exactly the same way. If I have 5x squared plus 7x plus 3, and I add 6x squared plus 2x plus 9, I can line them up just like I did with whole numbers. Oops. Come on. There we go. 5x squared plus 7x plus 3. Then here I'm going to put the 6x squared under the 5x squared, lining up the place values. The 2x under the 7x, and the 9 ones under the 3 ones, and we are adding down the columns. So 3 plus 9 is 12. Now here's one of our first differences with algebraic numbers. The first one we saw was they always have to be out in long form. We can't abbreviate them like we did with whole numbers. We could abbreviate a whole number just because we know the place value just by its location in the number. Algebraic numbers, we always have to write them out with the place values. Second is we can have more than one digit in a single place value. We never carry with algebraic numbers. So 3 plus 9 is 12. It's a positive 12, so I put a plus with it. 7x plus 2x is 9x. Again, it's positive, so put a plus there. 5x squared plus 6x squared is 11. And we keep the same name, x squared. Where it gets confusing is when we get negatives in it. Each digit in an algebraic number can be positive or negative. In a whole number, or an integer, if I have a negative 237, either every digit is negative, that'd be a negative 2 hundreds, and a negative 3 tens, and a negative 7 ones, or every digit is positive. In an algebraic number, each digit can be positive or negative on its own. I might have 3x squared minus 9x plus 12, where you can see that the x digit there, the negative 9x, is negative and every other digit is positive. So if I add that to 5x squared plus 7x minus 3, well, once again, I'll line it up. 3x squared minus 9x plus 12. I line up the 5x squared with the 3x squared. My positive 7x with my negative 9x. And my negative 3 ones with my positive 12 ones. I am still adding here. 12 plus negative 3. Positive 9. Negative 9x plus positive 7x. So negative 9 plus positive 7 is negative 2. We keep the x. 3x squared plus 5x squared, 8x squared. So I told you that subtraction was where the integers would haunt us. Let's take a peek. So 3x squared minus 9x plus 4 minus 7x squared plus 12x minus 7. So we're subtracting here. Let's set this up. 3x squared minus 9x plus 4. I'm going to put the 7x squared under the 3x squared. Positive 12x under the negative 9x. And then negative 7 ones under the positive 4 ones. And now we are subtracting down the columns. Well, 4 minus the negative 7, I'm going to write that off to the side. 4 minus the negative 7 is the same as 4 plus 7, which is positive 11. Negative 9x minus 12x. Well, negative 9 minus 12 is negative 9 plus a negative 12, which is negative 21. We keep the x. 3x squared minus 7x squared. 3 minus 7 is negative 4. And you keep the name of x squared. What do you think? Good stuff? Let's take a peek at something like this. We multiply the counts. What's 3 times 9? 27. Multiply the names. X squared times x to the 5th is x to the 7th. When we're multiplying exponents with the same base, both of those have a base of x. We add powers. If we add more than one variable, I'm going to have 5x to the 5th y squared times 4x to the 3rd y to the 3rd. Well, I multiply the counts. What's 5 times 4? 20. X to the 5th times x to the 3rd. X to the 8th. Y squared times y to the 3rd. Y to the 5th. That's pretty straightforward. Where things differ from what you've seen before is when we hit multiplication with more than single-digit numbers. Things like this. You've been taught a shortcut, which we'll get back to. But if this were numbers, if this were like 3 times 47, we would set it up as 47 times 3. You'd do 3 times 7 and 3 times 4 and go on, right? Well, the same works here. This is 7x minus 3 times 5x. Well, 5x times negative 3 is negative 15x. 5x times 7x, 35. 5 times 7 is 35. X times x is x squared. That is the full multiplication. Looks exactly like multiplying whole numbers. Now, of course, we've all been taught a shortcut called distributing. If you distribute here, you just leave it, all it does is save space. You do 5x times 7x, which is 35x squared, and 5x times negative 3, which is negative 15x. Just saves a little space. The one that really frustrates me is this one. We have x plus 7 times 2x minus 5. You were taught a shortcut called FOIL, most of you, right? We'll come back to that. What really is going on here is you're just multiplying 2-digit numbers. X plus 7 times 2x minus 5, and you're multiplying. So negative 5 times 7 is negative 35. Negative 5 times x, think of that as a 1x. That's just negative 5x. 2x times 7, positive 14x. And 2x times x, 2x squared. Then we add. We got negative 35. Negative 5 and positive 14 is a positive 9x and 2x squared. That looks just like multiplying whole numbers. Well, again, you were probably taught a shortcut. FOIL, F stood for first. Multiply the first digits. X times 2x is 2x squared. O stood for outer or outside. X times negative 5 is negative 5x. I stood for inside or inner. So you do the inside digits. 7 times 2x. Well, most books taught you to just put it over here, but it's going to be 14x. So I'm going to put it under the 5x so I remember to combine those. Then L stood for last. You combine the last digits. 7 and negative 5 is a negative 35. And then we add those. I've got negative 35. Negative 5x and positive 14 is a positive 9x and 2x squared. It's just a shortcut is all it is. For right now, we'll come back and look at more of this later. We're going to give you some homework to work on. We're going to look at Big Book. Page 256, 257. This is the unit exercises. 1 through 75, the odds. And then, of course, page 389 through 390. This is exercise 13-2. And page 392 through 393. Exercise 13-3, and again, do just the odds.